Okay, we're at paired t-tests, which are the final two formulas on your yellow sheet. So we are down in the bottom half with means, and we've got paired samples. So there's a formula for the confidence interval, and there's a formula for hypothesis testing. So we made it through the entire list. Maybe you weren't sure if we could do it, but we did. We did. I have had every confidence in you. So chapter 25 is paired t-tests. So we're still working with means because we're working with t-tests. But now we have two samples that are not independent of each other, but there's a very careful one-to-one matching between the samples. So maybe it's the same person who's measured twice. So at the beginning of a diet and the end of a diet, did that person lose weight? Or two measurements within a person. So maybe you put placebo in one eye and eye drops in the other and see which eye is less dry or less red. So two measurements on the same person, either at different points in time, or put one kind of hand lotion on one hand and the other kind of hand lotion on the other and see what difference it makes. So two measurements somehow or other on the same person. Or twins, especially identical twins. They have the same genetics, and so if you randomly assign one twin to a new blood pressure drug and the other twin to a placebo, then you know that it's not genetics affecting the difference between the two, but hopefully the treatment. Of course, there are lurking variables of lifestyle then and that sort of thing, but at least you've knocked out the huge effect of genetics. Or carefully matched people. Match on age, health status, that sort of thing. Okay, so you can carefully match two individuals, and then one gets the drug, one gets a placebo, or you just look for differences between the groups. On the study I worked in Pittsburgh, that studying women going through menopause, we measured all kinds of things at the beginning of the study, and then when a woman would go through menopause, we would pull her back in and measure all these things again. But now if there was a change, we don't know, of course, if it's because of menopause or because she's, say, 5 years older. So we used a paired design. We would find a woman in the study who was the exact same age as the woman who went through menopause but had not gone through menopause. Then say if the blood pressure of the woman who simply got 5 years older went up this much, and the blood pressure of the woman who got 5 years older and went through menopause went up this much, well, then we start wondering if this is the amount of increase that's due to menopause. So carefully paired observations in that case by age. So two sample t-test is where we have two completely separate groups, and paired are where we have two carefully matched observations. So, for example, let's say we want to compare the average fat in Domino's and Papa John's pizzas. So two possible study designs are randomly choose 20 pizzas from each place and measure the fat content of each pizza, or alternately measure the fat content of a pepperoni pizza from each place, and then a vegetable pizza from each place, and a supreme pizza from each place, and so on. So the first one, randomly choosing 20 pizzas from each place, would be analyzed using what? Two sample t-test or paired t-test? Well, that would be a two sample t-test, because now we randomly selected a bunch of pizzas from Domino's and a bunch of pizzas from Papa John's. No matching or pairing, just randomly selected a bunch of pizzas from each. The second one would be analyzed using a paired t-test, because now we're carefully pairing by kind of pizza. So a pepperoni from each place and a mushroom from each place, and so on. So the second one is obviously a lot more precise. The first one, just by chance, we could end up with 20 meat lovers pizzas from one place and 20 vegetarian pizzas from the other. And obviously a lot of bias would have been introduced. It wouldn't be a fair comparison. Whereas the paired design, that's a very fair comparison, because now we're comparing like to like. So paired t-tests give us additional precision. The assumptions of the paired t-test are that our samples are paired. We have this careful one-to-one matching. some sort of randomization was used. Either if we have two measurements on one person, that those people were either picked at random, or we assigned a treatment randomly within that person. So first they get the drug and second they get the placebo, decided at random. So randomization was used somehow or other. And then we also assumed that the difference between the pairs has a normal distribution with no outliers. So with the paired t-test, we are looking at the difference between pairs. So let's think about, say, a diet. If we have a group of people, and we measure their weight at time 1, so 100, 150, 200, 180, 250, and so on. If we were analyzing this right here, we'd use a one sample t-test. We're measuring one group of people once. One sample t-test. What on average do these people weigh? If we had two completely separate groups of people, so we measured one group of people at the beginning of a study and we measured a completely different group of people at the end. So we, say, put an entire city on a diet and we took 100 people at the beginning and a different 100 people randomly selected at the end. That would be a two sample t-test. Two completely separate samples, randomly picking some at the beginning and some at a different point in time. But if we have a paired samples t-test, then we're measuring the same people at 2 points. So we measure person 1 at time 1 and again at time 2. We measure person 2 at both times. We measure person 3, they gained weight. We measure person 4, and so on. So with a paired t-test, we're not looking at their weight at time 1 or their weight at time 2. We're looking at the difference. So 10 pounds, 20 pounds, they gained 20, lost 10. So this is how much did they lose? Okay, and so on. So with a paired t-test, we don't worry about this, we don't worry about this, we're just looking at this. So we compute the average of all those differences, and we compute the standard deviation of all those differences, and we compute n as the number of pairs, and then we have everything we need for our formulas. So our notation is D with a bar on top of it. D bar is the average difference between the pairs in our sample. SD is the standard deviation of these differences in our sample, and n is the number of pairs. So then first, hypothesis testing. Hypothesis testing is what we use, of course, if we want to know, is there an average difference? Or is that average difference 0? Is the average difference between the pairs 0, there is no difference on average, or is there some sort of a difference? So our null hypothesis is always equal to, and it's always that there's nothing going on. So in this case, nothing going on would be no difference on average. No difference on average between the pairs. And then the alternate, is there some sort of a difference? Positive, negative, or just some sort of a difference. Then our test statistic is the t-statistic. So remember, that's always comparing what we see in our samples to what we hypothesized. So what we saw in our samples is the average difference between pairs in our samples, minus an implied 0, because we're hypothesizing that there is no difference relative to the standard error. So we compute that, and then we go to table T and find the p-value, just like we did in chapters 23 and 24, and then we make a decision, just like before. So a lot of this is review. So let's try one. So a World Health Organization article based on an English study. They wondered if a tax on sugar added to beverages in England in 2018 led to less added sugar in beverages. So they found beverages that existed in 2014 and 2018, so they could use a paired study. Same beverage, Gatorade or whatever, measured twice, 2014 and 2018. So they randomly selected 30 beverages that existed in both 2014 and 2018. The null hypothesis is there is no change in sugar content. No change in sugar content. On average, that tax had absolutely no effect, or if there is a drop, we don't know exactly what that's due to, but the tax would be one possible explanation for a drop in sugar. And then the alternate, well, let's say our difference, we're going 2014 minus 2018. Well, if there's been a drop, then it was higher in 2014 than 2018. So the difference, 2014 minus 2018, would be positive. So our alternate, if we're subtracting that way, is that on average the difference is 0. On average, sugar dropped. And then we need our t-statistic. Well, on average, the sugar content dropped 3.8 grams over time. Now, I have to admit I'm making up the standard deviation to try to get results similar to what they got, because they unfortunately did not report it. So I'm saying that's 3 grams and 30 beverages measured twice. What was their sugar content in 2014 and again in 2018? So our t-statistic is 6.938. Okay, so we have our hypotheses, what we're claiming is true about the population of all beverages, right? So we're talking about the population of all beverages in England that, I guess in this case, existed in 2014 and 2018. Now we need to find the p-value. Well, we have a t-statistic, so we're going to go to table T. We have 30 pairs, so we're going to have degrees of freedom equal to 29. 30 pairs minus 1 gives us 29 degrees of freedom. Our alternate is greater than, so that is one-sided. So let's go to table T and find out what we've got. So degrees of freedom are over here on the left. So we have 29 degrees of freedom. And then when we have 29 degrees of freedom, we need to find our t-statistic. Well, our t-statistic is off the charts, 6.938. If we go this way, 6.938 is somewhere over here. Maybe, in fact, it's off the paper. It's so big. 6.938. P-values, remember, we go to the top of the page to find. So we're going to be over here with our t-statistic. Go to the top of the page. Our alternate is one-sided. As we move in this direction, our p-values are getting smaller. So we don't know what the p-value is out here, but we know it's less than 0.005. So it is less than that smallest p-value of 0.005. Well, no matter what our alpha is, 0.01, 0.05, or 0.10, our p-value is less than that. So we reject the null hypothesis. We believe the alternate, that on average sugar content in beverages has dropped significantly in England over that 4-year period. So it was a yes/no question. Has sugar content dropped significantly? And we say yes, yes, yes. We can't say, of course, that is due to that tax on sugar. That's one possible explanation. All we can say is that we're pretty sure. Now, of course, if we reject the null hypothesis incorrectly, we've made a type 1 error. If there really was no change in sugar content, but based on our sample, we just happened to get drinks in our sample where there was a drop. So we could have made a type 1 error. We have to admit that. But probably there's been a significant drop in sugar over those 4 years of time. Okay, now let's say we want to know how big is that average drop? How big is that average drop? Well, now we want a confidence interval. A confidence interval. So how big is the average change, the average drop for all beverages and sugar content? Well, we'll use the confidence interval formula, which is the average difference plus or minus some t-statistic times the standard deviation of differences over the square root of n. So we just need to find those 4 numbers. 3 of them we get from our sample. The average drop was 3.8. Now we need a t-statistic. We're not going to use that 6.9. That would have the wrong level of confidence. So we're going to go back to table T, look up 29 degrees of freedom, because we had a sample size of 30. And then it depends on our level of confidence. So if we want 95% confidence, remember the confidence level is at the bottom, p-values are at the top. So 95% confidence, 29 degrees of freedom. So our t-statistic is 2.045. 2.045 for 95% confidence, 29 degrees of freedom. With a standard deviation of 3, we're assuming, and a square root of 30, sample size of 30. So we get 3.8 grams. That was the average drop in our sample, plus or minus our t-statistic from table T times our standard deviation of the difference in sugar over time over the square root of n. So 3.8 plus or minus 1.1. Subtract first and we get 2.7. Add and we get 4.9. So we think the average drop in sugar is somewhere between 2.7 and 4.9 grams. So our average difference in our sample is 3.8. Our margin of error is 1.1 gram. That 1.1 tells us how close we think this 3.8 is to the true difference in sugar, the true drop in sugar content. So we think 3.8, well, that's based on our samples, and we think that's within 1.1 grams of the truth. Probably. We're not 100% sure, of course, with statistics. 95% confidence. We're only 95% confident that we caught it. So here's our confidence interval. So we are 95% confident that the average change, the average drop in sugar, in added sugar, in all beverages in England is between 2.7 and 4.9 grams. So the change in the population of beverages in England between 2014 and 2018, we think, so we're 95% confident, not 100% confident, we're 95% confident that the average drop in sugar in all beverages in England is between 2.7 and 4.9 grams. And we knew it was a drop because we have an entirely positive confidence interval, and we subtracted 2014 minus 2018. But in order to end up with a positive number, we have to take bigger minus smaller. Bigger minus smaller gives us a positive number. So we know there's a significant drop. There's no 0 in there. If there's a 0 in there, then we'd say there was no significant change in sugar content. So there's no 0 in there. We know there's a significant change. In this case, we know there's a significant drop because the whole confidence interval is positive, and we were subtracting in this direction. So we're pretty sure that the average change, the average drop, is somewhere in this range. Now, obviously, some of our beverages may have increased in sugar. Others dropped by way more than this. So we're talking about the average drop of all beverages. We're not talking about individuals. We're not talking about other sample. If we took other samples, what the average drop of those samples would be. We're just saying we think the true drop of all beverages in England in added sugar is somewhere in this range. The average drop is in there. So pair t-test. We have two groups where there's a careful one-to-one matching, and we're wondering if there's on average a difference between the pairs. So is there a difference on average? Hypothesis testing. How big is the average change, the average difference between pairs? Confidence interval.